can still hear me, Teseo? So, welcome. Do we have sound? Yes, okay. So welcome everybody back to our course, to the attendees from yesterday and also to new viewers. Today we will continue with our tutorial on black box geometric computing with Python. And let me first quickly show you the accompanying website for our course, where you can find all the course material. So the domain of the website is geometryprocessing.github.io, and then blackbox-computing-python, and there you can find all the material. You find all the videos. If in case you missed some from yesterday, you can watch the videos on FEM introduction. You can look at the static notebooks there, and you can also find the Jupyter notebooks, launch them in Binder or download them, and also have direct links to the notebooks. Besides, we have installation instructions and further descriptions on the packages and the motivation behind the course. In the following session, we will now work on the CAD deep learning example, and you will directly find this static version of this notebook here, or you can try to launch the Binder, which I can quickly show you as well. So this is the Binder notebook that you find, and if you want to follow the course more interactively, you can launch this notebook on Binder or with Jupyter, and then just run the cells by yourself and have fun following the course in this interactive way. So let me now quickly also show you the static version here, in case you just want to read the code and look at the results. You can also just follow the static HTML version. So with this, enjoy the tutorial, and we will have questions and answers again after the video. Have fun. Putting the data. In this tutorial, we will train a machine learning model on computer-aided design data. This is more a hands-on approach, so we will not cover much of machine learning theory. Instead, we will follow a full pipeline on training a model, loading the data, visualizing the features, and analyzing the results. So if you're interested in more theory about machine learning, you should check out one of the many available online courses. So let's dive right into. For our CAD data that we're using, we use the ABC dataset. This dataset is a dataset of 1 million CAD models, or computer-aided design models, and it brings with it a lot of features that we can use for machine learning. We will learn about this in a few minutes. So you can acquire the ABC or download the ABC dataset from deepgeometry.github.io and then ABC dataset, or just search for ABC dataset and you will find it. Let's see. So for reading the data, we need a few libraries again. For example, we need the YAML library and then libIGL for processing, NumPy for data representation, and Meshplot for visualizing the data. So let's see. If we have downloaded the ABC dataset, there are different channels. In this case, we just make use of the OBJ or object channel as well as the feature channel. And if we want to load our data for training a machine learning model, we now need to load the models. And we can do this by defining such a simple read model function. We make use of read OBJ from libIGL. And then we read out all the vertices, the normals, the phase indices, and normal indices that we get from this libIGL function, as well as the features we get from the features file, and we load these with YAML. So once they are loaded, we just put everything into a dictionary and we return it. Let's call this read model function on one of the models from ABC, and now we see we get, for example, 20,000 vertices in this model, 40,000 faces roughly, and our feature dictionary contains two keys. One are the curves and the other feature description are the surfaces. So there are two lists basically in there that describe features on curves and features on surfaces. We'll see about this in a minute again. So the first feature of the ABC dataset that I want to present are surface normals. We will also use this as one feature for training a machine learning model later. Let's first execute the code and then go through it line by line. So these are the surface normals for the model that I just loaded here in color coding. So this is the model with 20,000 vertices and 40,000 faces roughly. What we are doing here first is averaging the normals, since the ABC dataset brings normals for all the vertices, but on these sharp edges here, for example, there are actually two normals defined for each of the vertices. So what we're doing here in this averaging step is just averaging the possibly n normals of all the vertices and creating one normal for those. Let's quickly see. See the directions with vector visualization. So we see that on these edges, the normals, then the average normals are actually pointing diagonal away from the edges. This is one way of defining it. There could be other ways of defining it. Okay, and this is one of the features that we're gonna train a machine learning model later on. So what we input into the model are then point clouds, and we get out surface normals for each of the points in our point clouds. What we can do to compare this are the calculation of surface normals with libIGL. So if we calculate normals with libIGL, we hand in our surface model, the vertices and faces, and then we get back our normals that are estimated just from the faces and vertices. And we can compare those with the ground truth normals, and we see that they slightly differ from the actual ground truth. So the black normals are the ground truth normals we get from the parametric surface description that comes with the CAD file. And the red normals are the ones we estimate just from the vertices and faces, which we can, for example, then use later for analyzing the machine learning results to compare them to such a traditional approach. Another feature we want to train a machine learning model later on are sharp edges or curves. ABC brings this with it as well. So let's see how this looks. So this is the same model again, but now with the sharp features or sharp edges. So as you can see, the black parts, these are all sharp edges or curves, and they are basically defined by two adjacent patches, or the normals of two adjacent patches differ by a certain degree. Then the edge is defined as sharp, and if they don't differ by a certain degree, then the edge is not sharp. So you can see here, for example, when two adjacent patches are connected with such a round corner, there's no sharp feature. Whereas if they are really going into each other by a 90-degree angle, it is defined as a sharp feature. Okay, so the code in order to generate this as ground truth data for the learning model is the following. We just go through our curves list in our features, and then for each of the curves we have a flag that tells us if the feature or edge is sharp, and then we can add the vertices of this edge into a lines array, and these lines we can then later add to our plot, for example, or to our ground truth for the machine learning. So as there are many more point-based machine learning models, we can also generate the same data for point cloud-based models, and this is how it looks like. So we again go through our curves list and then check if one of the curves or edges is sharp. If it is, we just set the according vertex class to 1, whereas all other vertices are set to 0. So we, for a classification task, a possible one, we have two classes: a sharp class, which is 1, as well as a other class, which is 0. And if we visualize this, we see that all vertices on the sharp features or sharp curves, sharp edges, they carry the class 1, whereas all other vertices on round edges, for example, or on surface patches, they are belonging to class 0. Another feature in ABC are surface patch types. So as these models are defined by parametric surface patches, each of these patches has a certain type. And the types can be, for example, a plane, a cylinder, a cone, sphere, a B-spline patch, and so on. So what we can also train here is a machine learning model that estimates the surface patch types for a point cloud, for example. In order to get the ground truth labels here, we again go over our feature file, but in this case we don't go over the curves, but instead we iterate over the surfaces. So for each of the surfaces we can just get the class here by mapping the surface type into these numbers. So plane would be then class 0, whereas a B-spline surface would have the class 6. Once we have this, we have assigned one patch class per vertex again, and we can visualize this here, and we see that, for example, these green parts here, they are cylindrical surface patches, whereas the yellow parts are planar surface patches, and so on. Here we have, for example, a cone surface patch, and this is a B-spline surface patch. The same applies again for point clouds. So since these point cloud machine learning models are much more sophisticated already, we want to train such a model on point clouds. So we can also estimate the surface patch type per point cloud, per point in a point cloud, and then we can train a machine learning model with these ground truth data labels. Okay, so we've just seen all the data that we want to train our machine learning models on now. And for the machine learning itself, we also need to set up some libraries. So what we want to use for our example are PyTorch and PyTorch Geometric for training these two different models. The first model will be trained on these sharp curves or edges, and the second model will be trained on normal estimation. And for both we can just use plain PyTorch with the extension of PyTorch Geometric that gives us these point cloud networks, point cloud processing networks. So you can install them according to their documentation. Once we've installed these libraries, we can import them just by importing some torch libraries. So we need some functional parts, and we need a few layers that we can use later for defining our network. Also from PyTorch Geometric, we need some transforms, data loaders, as well as this dynamic edge convolution layer that we also use for our network. Additionally, we need this multi-layer perceptron, which I will talk a little bit about later again, and an ABC dataset class, which is basically a class for loading the ABC data. So let's first see how we can actually load the data into memory. And for this, I'm just running the cell since it takes a little while, and then I'm going to talk about what the different lines do. So here in the top, we have a few transformations. So this is a transformation that we apply to our training data. Then we have a transformation we apply to our test data, and we have a pre-transformation that is applied to all the data. And then we have the ABC dataset class here that we use to load our data into memory. This takes a little longer the first time we run it, since all the data is processed then and transformed in a format that it can be loaded faster later. So what we hand into this class is just the path to the OBJ and feature files. Then we hand in the type. The types are normals for surface normal estimation, edges for this sharp edge estimation or detection, as well as types for detecting the surface patch types. The next parameter of this ABC dataset class then is telling it whether it's a train or testing dataset. So true is the training dataset, false is the testing dataset. And then we hand in these transformations that I just mentioned. So we have a pre-transformation as well as a transformation that is run before putting our data later into our model. So the pre-transformation can be seen as a transformation that is applied to all data once, and then the data is stored in this transformed form. And this pre-transformation is just a normalized scale. So since all the data comes with different scales from ABC, we just want to normalize the scale so that all point clouds that we load in are normalized to the unit sphere, or to be inside of the unit sphere. Okay, so this is the pre-transformation. Then for the training and testing, we have different transformations. For the trainings, we just subsample our data to be 5,000 points. So each of the point clouds that we've put into our network is 5,000 points large. If for larger models, for example, it's subsampled to 5,000. For smaller models that have less points, it's upsampled to 5,000. So some points are actually duplicated. The next transform we apply then here is just a random translation of a certain amount here, and then we add 3 random rotations by maximum 15 degree to all 3 axes. Okay, and once this is run, we have then our training data set for normals, as well as our training data set for edges, and testing data set for normals and testing data set for edges. With this data loaded, we first maybe want to quickly look into the statistics of our data and visualize also some data. So let me first run this, and we can see here now we have in our testing data set, and in this case it's the testing data set for the sharp edges or curves, we have 500 models in there, so it's rather small. It's not all of the ABC data. But for the testing, it's still fine. Also, the training dataset has, in this example, just 500 models. So it's really just a subset to make it feasible to load it here in real time. Next, we see that this dataset, the edges, has just 2 classes, which are sharp feature or not sharp feature. This we can just get here this information by calling length of dataset. And the number of classes we get by calling dataset num of classes. What we get next or calculate next here are the amount of classes or the percentages of each of the classes in our data. So here we can see that 93% of our points in our point clouds of these 500 models are actually labeled as non-sharp. So this is all the yellow points of the point cloud. We see that if we zoom in here, it's actually a point cloud, and these points are plotted on top of each other. And 7% of the labels are of class 1. These are these sharp curves here. Okay, so we have some imbalance in the data, but this is not a huge problem, as we see later that it still works, and there are also techniques that can be used for dealing with such imbalanced data sets. What we get next here are the shape of our models. So for example, this model here contains roughly 20,000 vertices, and the labels for sure are also then one label per point or per vertex. If we look into example the training data set, so trained data set for the normals, the same model, we can also plot this and see how this looks like. So this is the information about what we've seen before, but this visualization here is for the normals now, and we see that in the training data set we really have these 5,000 points, and we see that the normals are pointing into different directions. So this visualization here for the training data set, it's not really meaningful, since 5,000 points are just not enough to actually get a feel how the normals behave. So let's do the same for the testing data set. And here we see that we can really see that the normals are properly defined in our ground truth. They point into different directions. Once we visualized our data and looked into the statistics, we can actually define the network that we use for our training and prediction. So in this case we are making use of a network called Dynamic Graph CNN, which is one of the networks that works on point clouds of arbitrary sizes. So this network basically has a few parameters to set. One parameter is, for example, the nearest neighbor definition. So here with this k parameter we tell how many neighbors make up this graph that is used inside of the network. And we see that we are setting up 3 layers of this, 3 dynamic edge convolution layers, and they take this parameter, how many neighbors actually define or are used in this graph definition. And the other parameter is the aggregation parameter, so we use some max pooling here. The network consists then of these 3 dynamic edge convolution layers, 1 linear layer, which is just a multi-layer perceptron, and this is just a linear layer followed by ReLU and batch normalization. And these are in and out channels. And then we have another MLP network or sequential network that consists of 2 of these perceptrons with dropout layers in the end, and the output of our network will then be a linear layer with the amount of output channels. And for the edges, for example, this will just be 2 output channels for the 2 classes. The forward pass then of our network, and this is how the data is processed, takes all these parts that we defined up here and puts them together to our sequential network. So we just read in our data and we split this into position and batches. So position is basically the input data, the point position, and the batch to which batch belongs, this point, or to which model in the batch belongs this point. And then we have these 3 convolution layers that we run our in sequential order. We have the linear layer in the end, and then the output layer is this MLP layer. We get our data out then here from the MLP layer, and then we have to differentiate between what type of features we use here. So for the edge features, for example, we want to run a log softmax layer afterwards. for having a classification. This is also true for the types layer, whereas for the normals type, we want to have a normalization and just normalize the normal to unit length. So this is basically the definition of the network. And let's see what this dynamic edge convolution actually sort of does. So if I go back here quickly, so this dynamic edge actually builds a graph with k equals 30 nearest neighbors, and the graph is built dynamically in each of the layers. But just to get a feeling on how this actually looks for our data, here we're building such a k nearest neighbor graph with 6 neighbors, and for the model that we've seen before, this graph actually looks like the following. So we see that each of the points in our point cloud, and this point cloud here is really subsampled to just 1000 points, we have such a graph that each point has 6 neighbors, and this is the neighbor definition then later for running the convolutions. Okay, the visualization for this is just that we can access here this edge index and then we can visualize it. Just to give you a rough idea how this whole graph neighbor definition looks like in practice. The next task we do is to define a loss function for the training that we do later. So in this case we actually have 2 loss functions that we want to use. The first loss function can be just used from PyTorch, and this is just basic classification loss function. So we use cross entropy loss for the curve or sharp curve, sharp edge classification, as well as for the surface patch classification we can also use this cross entropy loss function. For the normals instead we need to define our own loss function, and this can be done as follows. So here we just define a class cosine loss, and this inherits from a torch module. We have this constructor here, and then the actual code goes into the forward function here. What we define here is not just the loss, but also some sort of accuracy measurement for later running the training to have an accuracy value to plot. Okay, so the loss itself we calculate by just taking the dot product of the 2 normals. So x is, for example, the estimated normal, and y is the ground truth normal. So what we are doing here is taking a torch multiplication of x and y, and then summing it up along the axis 1, and this gives us a dot product of these 2 normals. And the dot product itself is sort of a measure for how well these 2 normals match. So if they are, for example, pointing into the same direction, this dot product will give us the value 1. If they are pointing exactly into opposite direction, the dot product will have the value -1. And if they are perpendicular or orthogonal to each other, the dot product will have the value 0. So what we are doing, we're not directly taking the dot product as loss. Instead, we are taking 1 minus, and then the power, the second power of the dot product. So this power function here actually changes the sign of the dot product. So normals that are pointing into opposite directions, they are considered as pointing into the same direction. In other words, we're just mapping the normals from the full sphere into a half sphere, and by doing this we're basically ignoring the direction of the normal. And in order to have a proper loss function, we're just subtracting this value here, which can be between 0 and 1 exactly, and we're subtracting this from 1. Since if this is 1, we actually have like the best match. The normal can either point into the opposite direction or into the exactly the same direction, and these both values will be 1. So we will have a loss of 0, whereas orthogonal normals that are like the most wrong they can be, they will have loss 1. and then we're just summing up over our normals in one of the point clouds, and this defines our loss function. For the accuracy instead, we are taking a little bit more complicated approach. So what we're doing here is we are just taking the absolute of our dot product, which also makes it invariant of the direction of the normal. What we are then doing is clamping it to the domain, or to the range from 0 to 1, to not have problems with this acos or inverse cosine here, since it could become undefined and could become none then later in the training. And then we are basically like calculating the actual angle of our normals, and we're summing up the angles and dividing it by the amount of angles or the amount of normals. So what we're getting here in our angle measurement are just basically the average angle deviation of all the normals. Let's quickly run this code, and now we have this cosine loss function that we can use in our training. So to define the training procedure, we also have to write a little bit of code. So we write this train function here, and this actually gets a train loader, which is a loader for our data set. So this can do shuffling and so on, so it's convenient to use such a loader. What we then need to do first is to switch into training mode. So we just call on our model to switch to training mode by calling this function train, and now we iterate over our training loader, and this does all the batching and shuffling and so on. What we do first then is we send the data to our device. In case of GPU, we send it to GPU. In case of CPU, it's basically already, or it's loaded then to CPU. Once the data is sent to the device, we can put it through our model for the training, but we first need to still like zero the gradient on our optimizer to not have values from the run before. The model itself then takes in the data, puts it through this network that we just defined, and then gives us an output, which are basically the predictions on our data. With these predictions, we need to differentiate again for the type. So if we have this edge or type, then we just have this cross entropy loss function here, and we put in the estimated normals as well as the edges and the ground truth labels here, which are in data.y. For the normals instead, we call this cosine loss function we just defined, again with the output normals that are normalized already, and then the ground truth normals. And we get back here the loss as well as the angle. Once we have calculated the loss, we can actually do backpropagation, and we do this just by calling this backward function. After the loss is backpropagated through our network, we can call this optimizer step and get the loss item and do some statistics on how well our network performs. So here we have to differentiate again between edges and normals. So for the edges, we just calculate the prediction. So we take this out max, which basically tells us which of the two classes has a higher value, and this is our prediction then. And then we calculate whether the prediction equals our data class, and we just sum it up and divide it here by the total number of nodes, and this gives us our accuracy. So it's the amount of correct nodes divided by the amount of total points or nodes in our point cloud. For the normals instead, we just take the angle and we convert it into degrees from radians, and then we take this as an accuracy measurement. So it's the mean angle deviation. And then we have this print statement here to just output the loss that we calculated here, as well as the accuracy that we calculated down here. Okay, let's run this code and do something similar for the testing procedure. It's just slightly different. So again, we define this function here. And here, instead of setting it to train, we need to set it to eval, so that none of the parameters of our networks are actually modified during this stage, and a few other things are happening there. Then we again go over our data batches in our loader. We need to send the data to the device and then set the torch to no grad, so that no gradients are calculated, and then we are running the data through our model again, get our outputs, and we differentiate for edges as well as for normals. So for edges, again, like before, we calculate the predicted class just by taking the max function. We calculate then the correct nodes by comparing the predictions to our ground truth data.y, and then we have our total nodes and the correct nodes. For the normals instead, we just calculate the angle, which is a measurement, or the mean angle deviation, which is a measurement for our accuracy. And again, we need to count the correct nodes by summing this up. Okay, and then give back the correct points divided by the total points. So finally we arrived at the actual training that we can run now, and here we for sure have to decide now between training an edge or training the network on edges, edge classification, or training the network on normal estimation. So let's first start with the edges. And here we load our train dataset as the edges train dataset and test dataset as test dataset, and we set the type to edges. What we define then is a data loader, and this takes our train dataset. The batch size for the training we set to 10, and we want to shuffle the training data as well to get better results. For the test loader instead, we set the batch size to 1, since the test models can be quite large point clouds, since we didn't subsample the point clouds in the definition of the training set. And here the shuffling we can set to false, since we don't care about it. We can actually take the data and put it through our network in the same order as it's defined in the data set. Okay, so the data is ready then. What we need to still decide as well is whether we want to calculate on GPU or on the CPU, and this we can define by this line. So here we set the device to CUDA in our case, since we have a GPU available. More important, we need to define our actual network, our model, and here we just initialize this net that we defined above or before, and we send this network as well to our device. So this is torch specific, we just need to send the network to the device where we actually do the calculation then as well. And the nearest neighbor graph we initialize to the value of 30, so each neighbor has 30 neighbors then in the graph for the convolutions. As an optimizer, we just use plain Adam with some learning rate here, and we also have a learning rate scheduler to modify the learning rate after 20 steps, for example. But these are just arbitrary settings here. They can be still tweaked to a large degree. So this defines then basically everything we need for the training. The training itself is then just a loop over the epochs. So we iterate from 1 to 100, for example, to have 100 training epochs. And then we call the training on our train loader. And then after training on one on all the data in our training set, we just run the test loader and we get the accuracy for the test, and then we can plot the accuracy as well. And after each epoch, we can actually save our trained model to have it available for later use and update the learning rate if necessary. So let's run this and see how this works for the edges. Takes a little while to load everything into memory and have it available. Now it's there and we are already running the training procedures. So here we have a training data set with 500 models or point clouds, and we have a batch size of 10, so we actually have like 50 batches to run through our network to have the training data processed once. And we see here that the loss is actually going down already during the training of the first epoch, and the accuracy is slightly going up or slowly going up, but it takes a little while. I mean, we have not yet processed even the training data once, and we see later that after already 50 epochs we have a good model to estimate the edges, for example. But I'm stopping this here right now, since this takes a little while, and we're gonna then load a pre-trained model soon. Okay, so I loaded the pre-trained model, and we're gonna look how training looks with this already pre-trained model, and I pre-trained this model for 72 epochs already, so not that much, but it already has learned something. Let's run the same code again, and now we're not setting our model here to initial values, but to the pre-trained values, and we see now that we are already at a loss of 0.01 or even less than 0.01, and the accuracy, which are the number of or the percentage of correctly predicted points, are already up to 97-98%. So most of the points are already classified correctly, and we can still train for more epochs. We can still use more training data to get even better results. Let's stop this again here and see the same training for the normals, and then we're gonna see how we load these pre-trained models and how well the models actually predict for our edge detection. So this is how we can load a pre-trained model that we've saved during the training process. So we just define here again what we want to load here. So we want to load our testing data set, and the pre-trained model we want to load has this file name here that we used before. What we do then is define our network with the number of classes of our according data set, and we just load the training state from this state file here, and we can then load the state dictionary into our model here by calling this load state dict function, and then we again send the model to the device where we want to do our calculation. We can run the same training now instead of for the edge classification or sharp edge detection, for the normal estimation. And we can do this just by switching here our data set. So instead of the type edges, we switch to the type normals, and then we also switch to the train data set normals and test data set normals. Afterwards, we also have to switch our network to use the different type, and in this case we're just switching to the type normals. Everything else can stay the same, and we can run this cell again, and we get a normal estimator by training this model here. So what's different now is that the loss represents a different loss, since we have this cosine loss that we defined. So here the loss defines how well the normals match the ground truth normals, and the accuracy represents the mean angle deviation. So we're starting about a deviation of 60 degrees for the first batch, and then the angle deviation mean goes slowly down. Sometimes it also hops up again, but overall after the multiple epochs of training it goes down to 10 degrees and even more. So let's stop here again and load a pre-trained model also for the normals and see how well this performs. You can also load a pre-trained model now for our normal estimator network, and we do this similar to what we've done for the edges. We just define the type here, our test set, and then the state file that we trained and stored our parameters to. So in this case we trained a network for 44 epochs for normal estimation, and the mean angle deviation at this state was 12.5 degrees on our test set. We do it similar now again. We just load the state file, which contains all the parameters that we trained so far, and we load this into our model, and we load the model to the device. So at this state we have our model ready for continue our training, and we just need to comment out here the redefinition of the model and can continue our training from this 44th epoch. And we see that our loss is already down by a large degree, and our accuracy now on these batches are 14, 15, 16 degrees of mean angle deviation. Finally, we've come to the point where we can visualize our prediction results. First, we do this for the normal estimation tasks, and later also for the sharp edge detection task. So for this we define another data loader on our test data set. We set the batch size to 1, and we set it shuffle to true to get random samples from our test set. We also call an iterator on our test loader to be able to call the loader.next function to get another point cloud sample for the estimation. So let's first run this first cell and now run a prediction on our test data set. And let's go through this code line by line. We set torch to no gradient mode, and then we run our data sample to the device and run it through the model to get our prediction in the out variable. Also, we need to get our ground truth values, and this we get just from our data sample. The position field in there are the vertices or the point cloud. We put this to our CPU and NumPy to be able to compare it and use it then in our further calculations. What we also need are the ground truth normals, and they are stored in this data.y field, so we just define y here the same way. Now we have normal estimations, so we look at this branch here, and the estimated normals are in the out variable that we get from our model prediction, and we store this as n, also on CPU and NumPy, and we convert these normals to colors here by just taking the absolute function of NumPy, and then we get color value 1 for the ground truth normals and color value 2 for the estimated or predicted normals. And we run this into our subplot function here with our vertices and then just the color which encodes the normal direction. And here we see on the left side our ground truth values, and then on the right side the predicted values, and we see that for this model it already works fairly well. There are still some outliers, but keep in mind that this model was only trained for 44 epochs, and the mean angle deviation is only at 12 degrees. So okay, so this is our next model, and on the left again the ground truth normals, and we see that on this model the estimator has much more problems than on the previous model. So there are parts of the model where the normals, for example here, are way off. In other parts it works better here, for example, and there. But this is one result that is less good than the result before. So let's see it for another model. So here we see the circular shape, and again it seems to work fairly well with some outliers. So here's another model that we floated and run through our estimator model, and we see that this model also works much better. Again, the estimation is much more precise. We can also look at the loss function here maybe. Okay, so here's a loss function that we can use for calculating the mean angle deviation. It's again the cosine loss that we defined before. We put in the out variable here, which is the estimation from our model, and then also the ground truth normals. And if we run this, we get back our angle, and we need to convert the angle to degrees to have it a meaningful value. So we see that for this model here, we get a mean angle deviation of roughly 50 degrees, which is still a lot, but the model is not fully trained. Let's also do the same evaluation for our sharp edge detection network. So again, we define a data loader on the test data set. In this example, we set shuffle to false to be able to access the same model that I've shown all over the tutorial, and the batch size again is set to 1 to make it estimate the results faster. So again, this loader, and now we can call the loader next function, and in this case we go into this edges case here, where we need to estimate the proper class just by taking the maximum over these two fields and then selecting the one with the highest estimation. Again, put it to the CPU and to NumPy to be able to work with it. And what we're doing here is some sort of color coding of the class again. So this is the first model of our test data set, and we see that for this model it does not work fairly well. One might argue that this is also a more difficult model because the edges are not super sharp. It's like a round, more or less round shape here where it doesn't work so well, and it's not super clear for the estimator if the edges are sharp or not. Let's load another model to see if it works better on easier models. So this is the next model, and here we see on the left side the ground truth again, and on the right side we see the estimation, and we see that for most of the curves the detection works fairly well. There are still some outliers on the patches themselves, and for some curves it doesn't work so well. This is the next model, and this is an easier one. So here we see that the sharp feature detection already works fairly well, with some exceptions. So at some parts the sharp estimation bleeds a little bit into the patches. Okay, so this is the model that I've shown before already. On the left side again we see the ground truth estimated sharp features, and on the right side we see the estimation from our network, and we see that in most parts of the model it works fairly well. It even detects this, or doesn't detect this curved part here, and the sharp features are almost all of them are in there. And keep in mind again that this model was also only trained on 500 models in our training data set. It was not seen by the network before. We just trained a few epochs, like 75 or so for this model, and there's still a lot to gain by just tuning the parameters, adding more data, and so on. So this brings us to the end of this tutorial, and we've seen that already with a few lines of code, the proper data loading code, setting up the network and the training structures, we can train a model that performs fairly well on two tasks for CAD. So that was the video about CAD processing for machine learning. Thanks for following our tutorial for today. Are there any questions? You can post them on the Discord channel or either on YouTube. Let's wait a few more minutes. questions so far. Probably most people are having dinner now. Okay, so there's one question about the amount of models in the ABC dataset and the amount of models that were used for training and testing. So for this example, we just used one chunk of ABC, and from this one chunk, we also just used 500 or 1,000 models. Otherwise, it would have taken too long to process all the data. But for sure, you can use up to 1 million models that come with ABC. But for most machine learning approaches, it's just not feasible to use that much data right now. So you would need to check which amount of data is suitable for your task and which amount you can actually process in practice. So there's a follow-up on this question, if it's really feasible to do it for the entire data set. And I don't think that it's, I mean, it would be feasible, you could do it, but it would just take very long. So in this example, as I've just shown, I ran the network on one NVIDIA Titan X for about 10 hours or so to train the network for these 70 to 100 epochs for 500 models. So you can do the math yourself. It would just take very long to do this processing. What you could consider is actually downscaling the size of the model. So what I've done here is just trained with point clouds of size 1000, I think, if I remember right. So there are a couple of things you could do to make it faster. The question is really about the application, what you're using it for, and it already shows that with not that many models you can train something that gives meaningful results. I think right now with the current state it's not feasible to do it for 1 million models. Any other questions? So, doesn't seem to be the case. Let's maybe wait 30 more seconds and then we can close the stream and hopefully see most of you again tomorrow for the last part of our tutorial, which will then finalize our course. If we consider features other than taking edges and normals, I hope you can still hear us. Yes. So yeah, there are other features you could, for example, consider the patch types, which is even more difficult than training for this sharp edge detection. That would be one feature you could do. You could also do something like instance segmentation, so segment into different patches. That would also be possible. Besides that, I think there could be other options to do. So right now, ABC doesn't bring any classes with it, but there might be some classification labels also available in the future for a subset of the ABC dataset, and with this you could also do classification. Other tasks would be just shape retrieval, so retrieving similar shapes by just using a point cloud and then querying the whole dataset. That would be another option. I hope that answered your question. Okay. No questions on Discord. Okay, so this question was also answered. If not, you can also always ask your question in the Discord channel and we will answer it offline. That's also possible, or use the session tomorrow with the last part of our tutorial and ask questions there. So thanks again for watching and see you tomorrow, hopefully. Bye-bye.